Here's where we're at, man. We've got our hierarchy filled out to this point. We kind of talked last time about, dude, this is all you need to know. If you have this stuff memorized, you will totally, totally, totally dominate the bottom because we talked about people's parents. So let's start first with the rectangle. Would you believe the rectangle in this family's tree, his parents are the isosceles trapezoid and the parallelogram? Like if those two got together and had a baby, they would have themselves a rectangle. Definition, I guarantee you'll get that right. What is the definition of a rectangle? Boom. 4 right angles. And then next is the symmetry lines. You know, the symmetry lines, you got to look at where it came from their parents. Let's see if the rectangle's even going to have any symmetry lines, right? Okay, here's, I don't care which one's mommy and daddy or whatever like that, but right here, does the parallelogram have any symmetry lines? Nope. Does the isosceles trapezoid have any symmetry lines? What do you think? Does it have any? It has one. So if either mom or dad has something like that going on, then the baby will have it. Will a rectangle have any symmetry lines? What do you think? Yes or no? Big fat yes. The question is where. It'll be in the same aspect of this. Would you believe the perpendicular bisector of the bases is, like if you go perpendicularly through that, that's where the symmetry line would be. Holy crap, dude. Help me. It's been a while. Where are the bases of a trapezoid? You know, I know it's isosceles, but what makes the bases the bases? The bases are the parallel sides. So question for you. Boop, boop. Are those sides parallel on a rectangle? Yes or no? Yep. So if I perpendicularly bisect those, I'm just going to kind of sketch one and don't do it. If I perpendicularly bisect those, wouldn't that be a symmetry line right there? Holy crap. Are these sides parallel to each other in a rectangle? So if I perpendicularly bisect those, wouldn't that also be a symmetry line in that case? How many symmetry lines does a rectangle have? 2. And here's where they're at. The perpendicular bisectors of the sides. There are 2 symmetry lines. The perpendicular bisector. Instead of saying the bases this time, we're going to call it the sides just because it's like, all right, it's like all of it. So there's the symmetry line. Last time we talked about peanut butter every day. Like, don't you have a big old capital B right here underneath this parallelogram because the diagonals bisect each other? And don't you have a big old capital E underneath here because the diagonals are equal to each other? Let's put them together. What should be true about the diagonals of a rectangle? It'll be this, right? What does it really mean? What does the B mean? They bisect each other. And what does the E mean? They are equal. Whatever order you want to put those in, I don't care. You could say they are equal and bisect each other, or you could say they bisect each other and are equal. Right? It's like they're both there. But to me, the diagonals is almost a freebie if you know peanut butter every day. Peanut butter every day. So this was your bisect each other, these were your equal, and this is your bisect each other and equal, or equal and bisect each other. So let's talk on this guy. Here's the rectangle that I have drawn. I've got a red diagonal and I've got a green diagonal. I'm going to ask you 3 questions. Question number 1, boop, is that angle right there 90 degrees? Discuss with neighbor. This is what's true about the diagonals. Let me switch colors. This is what's true. What word would need to be in there if they say that those would be intersecting at 90 degrees? Perpendicular. It's up there, right? That's not what I'm talking about. It's down here. Those are not. Here's the next question. Does the red one cut the green one into 2 equal pieces? And does the green one cut the red one into 2 equal pieces? What do you think? Yes, right here. Here's the last question. Is the red one the same length as the green one? What do you think? What word is in there that makes you say yes? They are equal. So how would I mark that? The red one and the green one are the same length, and they cut each other into 2 equal pieces. So should this be true? Bing, bing. Should that be true? Yep. What kind of markings do you want me to put on here? Singles, doubles, triples? What do you want? What do you think? Does that work? I'm going to make up a length. Pretend that is 5. How long should this guy be then? 5. Awesome. How long is the red one? Total length of the red one. How long is it? 10. How long should the green one be? It better be 10, right? So doesn't it also get cut into 2 equal pieces? So what's each piece? 5 and 5. So how many tick marks should I put on them? Singles, right? Would you agree that all of those are the same length in that case?
All right, so let's do some questions about rectangle, right? They tell us this guy is a rectangle right here. They say if the distance from A to C, that's this guy right here. Let's use a highlighter though. The distance from A to C is 2x plus 13, right? It's hard to put that in the picture because like they cut that guy off, you know? So I just know that he's like an entire diagonal right there. And the distance from D to B, he is the other diagonal, is 4x minus 1. They say find the distance from D to B. Well, that means we got to like solve for x and substitute in. So here's what we got. We got the diagonals of a rectangle. Going back to our hierarchy, we know that the diagonals are equal and bisect each other. So since these are the whole bad boys, I can just set them equal to each other and solve for x. So if I subtract 2x over, I have 2x minus 1. I'm going to add that 1 back over here. Get me a 2x, and then divide by 2, x should equal 7. But that's not what they ask us to do. They ask us to find the distance from D to B, so I need to substitute that bad boy back in. So I can do 4 times 7, so 4, clear, 4 times 7, and get this, and then subtract away the 1 in that case, and the distance from D to B, we'll write it like this, equals 27 in that case. We should get the same thing if we sub this guy back into the other guy. 2 times 7 is 14. 14 plus 13 is 27. So this is the answer to our question. We had to solve for x. Let's try that again. It says ABCD is a rectangle. Sweet. Uh-oh. The distance from A to E, he's just a little guy, right, is 3x plus 3. So we'll put him in the picture. And the distance from E to C is this dude right here, 5x minus 15. Well, those are on the diagonals, and according to my hierarchy, the diagonals are not only equal, but they also bisect each other. So all of those bad boys are the same in that case. So I can set these little guys equal to each other. 5x minus 15, and we will solve. So I need to subtract 3x over, and then I will add the 15 over, and divide by 2, and x turned out to be 9. They don't ask me for that. They ask me to find this from A to C. Uh-oh, A to C is like the whole thing. Well, what we can do is substitute 9 in for this. So we'll do 5 times 9 minus 15. 5 times 9, boom, minus 15. And that little dude right there is 30. Well, shouldn't this other guy be 30 in that case also? Because they're supposed to be the same. And if we just check, 3 times 9 is 27, plus 3 more. Yep, so sweet. The distance from A to C will be 60, because we had 30 plus the 30. So just reading carefully. All right, they say this bad boy is a rectangle. All right, here we go. One of our strugglers finding these angles. Measure of angle DAC. If you go and highlight, it goes from D to A to C, is 2x plus 4. So that little guy right there. And the measure of angle BAC, switching colors, please. Measure of angle BAC is 3x plus 1. Ooh, interesting. They say find the measure of angle BAC. Well, the question is, do we like set these equal to each other? And I guess the real question would be, like we would if this thing was a symmetry line, but he is not a symmetry line. Like a rectangle, the symmetry lines are like the perpendicular bisector of the bases, so that's not a symmetry line. But let's just kind of not lose sight of the basics. Like if this was a rectangle, this entire orange angle right here, shouldn't he be 90 degrees, right? You know, so like these two, they put together make that whole angle, so I need to add these two together and get 5x plus 5, and that should be 90, because that's what that whole angle measures right there. So that's a tricky one. And then I will subtract the 5 over, and then divide by 5. So 85 divided by 5 is 17. So we found x, but they want me to find the measure of angle BAC, right, because that's what they're asking me to do. So I will substitute that back in. It's 3 times 17. Boom, plus 1, and we will do the measure of angle BAC equals whatever this just said, 53 degrees in that case. So very tricky one. Don't forget the basics of a rectangle, that it's got 4 right angles by its definition.
Rhombus's definition is 4 equal sides. Right? You do that. The symmetry lines is the hard part for people until they figure out how these hierarchies marry together. The parents of the rhombus are the parallelogram and the kite. Since we're talking symmetry lines, let's look at these guys' symmetry lines. Old parallelogram had none. We get no symmetry action from the parallelogram. Nothing's happening from that guy. Don't we get all of our symmetry line stuff from the kite, right? Where is the symmetry line for the kite at? Through the what? Through the ends. You're going to have to refresh me. It's been like a long time since we talked about where are the ends of the kites. How do you know where those are at? Remember? Tell me why these are the ends of the kites. Why are those the ends of the kites? Tell me about those blue sides right there and these green sides right here. What's so great about them? That's where the two sides of the same do what? Touch each other, all right? You cool with, it's been a while. I used to make students write it on the hierarchy. If you want to write that on your hierarchy, the ends are where the two sides of the same touch each other at. Those are the ends of the kite. Every single kite, if you go draw a line through the ends, that's going to be a symmetry line. The symmetry lines are where two sides of the same touch. I'm just going to label these A, B, C, D. Please don't do that. You don't need to, but A, B, C, D. Question for you. In that rhombus right there, do two sides of the same touch each other at point A? Right here? Two sides of the same touch? Two sides of the same touch each other right there? If I was to draw a line through there, aren't those like the ends of this kite? Remember, rhombus is a kite, right? That was mother, so it's a kite. Isn't that a symmetry line right there? Another question. Do two sides of the same touch each other right here? Do two sides of the same touch each other right there? Do two sides of the same touch each other right there? So if I was to connect those together, wouldn't that be a symmetry line also in that case? How many symmetry lines does a rhombus have? Two. Where are they? Could you take I know I didn't draw them as lines, I drew them as segments. What the heck did I just draw in? Those two things, it starts with a D. Those two things are the what? The diagonals, right? Would you be down with the fact that there's two symmetry lines? They are the diagonals. The diagonals are the symmetry lines of a rhombus. And then let's go back to peanut butter every day. You got yourself a big fat P right here. You got yourself a big fat B right there. When you marry these together, for the diagonals, shouldn't the P and the B come together and give you some peanut butter in that case? What does P stand for? Those diagonals are what? Perpendicular. What does the B stand for? Bisect each other. So guess what's true about these diagonals? They perpendicularly bisect each other. Those diagonals perpendicularly bisect each other. You can use the symbol if you'd like. Perpendicularly bisect each other. All right, I'm going to ask you the three questions again. Here's my little rhombus drawn off to the side here. So, come on, man. Boom, 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 boom. Here's a red diagonal and a green diagonal. Question one, do those intersect at 90 degrees, yes or no? What do you think, yes or no? Yes, they do, because those diagonals are perpendicular. Does the red one cut the green one into two equal pieces? And does the green one cut the red one into two equal pieces? What do you think, yes or no? Come on, guys, I know we're tired. Yes or no? Yeah, they do. So I could go double, 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 double. Here's the last question before I mark that green guy. It's like, should I put double tick marks on it? Should I put triple tick marks on it? It's about this. Is the red one and the green one the same length? What do you think? Are they the same length? What word needs to be written in that blank for me to know they're the same length? They would have to be equal to each other. So they are not. So wouldn't this have to be triples and triples, Like this red one could be 5 and 5, and that green one would have to be 6 and 6. They cut each other into two equal pieces. They intersect at a 90, but they're not the same length. Let's go back to the worksheet.
So we got ourselves a rhombus here. It says find all the measures and all the side lengths and put the answer in the picture. There's lots of ways to get started here, man, but here's where I totally start is right here. Boom. The diagonals of a rhombus are perpendicular to each other. So I get all four of these, just like we did with the kite. And what we get on that is like right triangles everywhere, right? So here's our buddy. This side's 3, this side's 4. That hypotenuse will always turn out to be 5. And because this is a rhombus, all sides are the same, so all of these bad boys are 5. And then if we base ourselves off symmetry, the diagonals are a symmetry line, so this blue thing is a symmetry line, and this green thing is a symmetry line, so this guy's got to be 4 because that guy's 4, 3 to 3. And then let's do that with the angles, right? If this is 32, it's going to jump over that green symmetry line and be 32. But I could also jump over the blue symmetry line and realize that this dude and this dude, right, will have symmetry. And then same thing here. And then how do I find that other angle? Well, I have a right triangle, and this is 32, this is 90. We're just going to subtract 180, take away the 90, take away the 32, and that's 58. Remember, this is just like our kite problems, because a rhombus is always a kite because he's below him, but it's just fancier because we've got symmetry with both diagonals this time, right? So the rhombus is just like the kite, only faster. So here we go. ABCD is a rhombus. Yay. If the measure of angle ABD equals 60, so from A to B to D, right, is 60 degrees, find the measure of angle BDC. That would be this guy right here. Well, don't forget who this guy is. He's a rhombus, right? So the question is, like, how can I find this? You can do this so many ways, right? You can do this with the fact that you've got a symmetry line right here. So if I get my highlighter back, this dude is a symmetry line. So like this dude's totally 60. And then you can do that with this other guy being a symmetry line here, and this guy's 60. So that works. But the other thing you can remember is that this is also a parallelogram, bro. You know, it's like the rhombus is below the parallelogram, so those sides are parallel even though we don't really mark them that way. But you have parallel lines, and these are like alternate interior angles, but it doesn't matter. Symmetry works, so does parallel lines. It's all good in the neighborhood, but if I can get my delete button to work, that'd be awesome. But it didn't, so I'm just going to do this. That dude was 60 degrees. Cool. And then still got ourselves another rhombus. If the distance from A to E is 3x minus 1, bing. And the distance from A to C, where is that? Ooh, hold the phone. A to C is the whole big boy, right? It's 16. Find x. Fascinating. So this orange dude, A to E, is 3x minus 1, right? But the whole big boy, right? The whole big boy was 16. Well, these are on the diagonals. So I'm going to look to my hierarchy and see what's true about the diagonals. The diagonals perpendicularly bisect each other. So yes, that is true, but boom, boom, that should also be true. And then boom, 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 boom. They're not the same length though. But if that blue thing is 16, I'm not going to put a 16 in the picture. I'm going to put an 8 and an 8 because it got like bisected. And now for me to solve for x, like, aren't those like on the same expression? So like 3x minus 1 just equals 8, not 9, just equals 8. If I could get an 8 to work. Sorry about that. The reason why I put a 9 is because I was in my brain adding this 1 to both sides already and getting a 9 right there. And then I could divide by 3 and get myself a 3 on that dude. Cool. Just read carefully. Don't assume that they're giving you both little pieces. So ABCD is a rhombus. If the distance from A to B is 26, okay, so I got that in my picture. Doot. And the distance from B to D is 20, right? You know, find the distance from A to E. Interesting. B to D is 20. So let's put that in. And I don't really want to put a 20 in the picture. I'm going to do a 10 and a 10. That, to me, makes more sense, and I can only do that because the diagonals perpendicularly bisect each other. Hey, since I said perpendicularly bisect each other, I'm going to put that right angle box in there because I know that's going on. And look what they want me to find. They want me to find this blue thing, A to E. Well, look at what we got here. Isn't this our good old friend, the right triangle, where we know two sides? So 26 is the hypotenuse because he is across from the 90. I'm going to do the Pythagorean theorem, where 10 squared plus the distance from A to E squared should equal 26 squared. And then I'll do all this in my calculator. Well, I know 10 squared is 100. But 26 squared, 26 squared, I'm going to like punch that in. All right, so 26 to the second, that's 676. And then I need to subtract 100 away. So that will be 576. And then to get rid of that square, remember we will square root. So I need the square root of 576. And the distance from A to E is 24 in that case. So that was kind of neat. Don't forget that the Pythagorean theorem works on all right triangles, and when we have a rhombus, since the diagonals are perpendicular, we're going to have right triangles all over the place. Cool. So, and then this one here, it says draw a rhombus with your geometer, so we'll do that. That's shape number 9 on our geometer. Mark it by definition. Boom, 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 boom. Got it. The rhombus has a perimeter, sorry, there should be a space there, of 76. So all 4 of these sides add up to 76. So I can take 76 and divide it by 4 and get myself 19 back on that dude. Because 76 was what they should all add up to, and they're all the same. They have to just split up 4 equal ways. Then it says one diagonal is 34. So we'll draw that guy in. It doesn't really matter which one. So he's going to be 34. It says find its area. Whoa. If we go to the yellow card, I don't have the formula for area of a rhombus, so I could do parallelogram where area equals base times height. The problem is I don't have a height, right? The height would have to be the perpendicular distance between the bases, so no cool there. I could do area of a kite, but I need both diagonals. Ooh, let's maybe draw that other diagonal in and see what happens right here. So if I draw this dude in, right, now how do you feel about that 34 becoming the rhombus? The question is the blue one also 34? Or in other words, do the diagonals of a rhombus, or are the diagonals of a rhombus equal to each other? And they are not, right? So what we can do is we can maybe call this side X right here. And if we find it, shouldn't this be the same thing, right? Because, bro, those diagonals like perpendicularly bisect each other. And how can we find that little X? Well, here's our buddy again, right? Our buddy is the right triangle. So 19 is the hypotenuse, so I'm going to do X squared plus 17 squared equals 19 squared. And we'll punch these things in. 17 squared is 289. And 19 squared is 361. So to get x squared by itself, I need to subtract, right? So 361, take away 289, and that is 72. And then for us to solve for x, we will square root both sides, and that's not going to come out nice. Square root of 72, not nice. So we're going to leave him the square root of 72. Okay? But the whole reason that we found that is because we wanted to find the area of this guy right here. So I know that this is the square root of 72, and so is this, right? So what we can do is use the kites formula if we want, because I have both diagonals. It's 1/2 times diagonal 1 times diagonal 2, right? So, cool. We will sub in 1/2 times. I'm going to do this. I'm going to add these together. It's been a while since we've done it, but we can totally do it. 1 square root of 72 plus 1 more square root of 72 is 2 square roots of 72. And then the diagonal of the first dude is 34. And check this out. When I'm multiplying all these guys together, well, that's nice. I have 1/2 times 2, which is really just 1. So the area is going to be the square root of 72 times 34. I'm going to switch those around because that's just like the proper way to do it. 34 square roots of 72. And then we'll punch that in. 34 times the square root of 72. and I get me this guy right here, which will round to the nearest tenth, so about 288.5. About 288.5, and that would be in square feet. That was a wild problem, right? So I needed both diagonals so I could use the Kite's formula, and they gave me one, and because the diagonals bisect each other, perpendicularly bisect each other, we were in business with right triangles. So really,
this is it. It's finally time to do the bottom guy. Right? We got it all up here. Let's roll with the square. Please get his definition. Doesn't matter the order that you put them in. They both have to be there. 4 right angles and 4 equal sides. You know, if you say 4 equal sides and 4 right angles, same thing. It's all got to be there. I want to see how smart y'all are. Could you figure out the total number of symmetry lines that a square has from its parents, from him and from her? So we have decided that it will have some. Let's call this Mom over here. Mom has 2. Where are they at? That's over here. I'm on the rectangle. Rectangle has 2. It has the what? Perpendicular bisects the side. So I'm going to just roughly draw them in. I'll draw them in more accurate later. Wouldn't that be that one and that one? Those 2 green guys. How many does the rhombus have? 2. Are they the same ones as the rectangle, or are they different ones? They're different. Who are they? The diagonals. So if I could draw it in, how many total symmetry lines does that guy have? 4. Accidentally, sometimes when people draw the lines, they count up all these arrowheads, and there's 8 arrowheads. You know, it doesn't have 8 symmetry lines. Would you believe there's only 4? But there's going to be 8 arrowheads because each line has 2 arrowheads, right? So it's got 4. Where will they be at? So easy, guys. So easy. You put this in there, meow. You put the perpendicular bisectors of the sides, and you put this in there, the diagonals. They just get married together. So there's your 4 symmetry lines. They are the diagonals and the perpendicular bisectors of the sides, or the other way around. You just put it all in there. If you know rhombus symmetry lines and you know rectangle symmetry lines, you put them together. So 4 total, boom, you'll put that guy, bam, and then you'll say the diagonals, okay, that came from here, and the perpendicular bisectors of the sides, boom, that came from there. Again, like I said, if you switch that order around, that's cool. And here's where we're at with our peanut butter every day. We got some peanut butter going on over here. We got some butter every day going on over here. I'm going to put them together. Should these diagonals of a square be perpendicular to each other? Yes or no? Yep. Should they bisect each other? Yes or no? Yep. Should they be equal? So put them together. The diagonals perpendicularly bisect each other and are equal. Are equal and perpendicularly bisect each other, or the other way around. They are equal and perpendicularly bisect each other. They are equal and perpendicularly bisect each other. For the last time, I'm going to ask you those same 3 questions. Here's my square with a red diagonal and a green diagonal. Question 1, do they intersect at a 90? Yes or no? Yep, right there. Question 2, does the green one cut the red one into 2 equal pieces, and does the red one cut the green one into 2 equal pieces? Yes or no? Yes, bisect each other. So, boom. Is the red one and the green one the same length? Yes or no? Yes. This is the only one that you can say yes to all 3 of those questions. It's got the P, it's got the B, and it's got the E. If I could go back to the early 2000s, this is as close to Stacy's mom as you got. Because Stacy's mom has what? Got it going on. The square has everything, dude, you know. The diagonals are perpendicular. They are bisecting each other. They are equal. The square is the king of this family tree, right? Isn't it the most specific thing that you got? So there you go. Again, I told you, here's your P, here's your B, here's your E, right? What was true about these diagonals? We didn't talk about it too much in this class. I did it in the other one. What's true about those diagonals? Was there any PBs or E's or anything going on? Was there anything fancy at all? Nothing fancy. So you can handle that. Then you marry them together. These diagonals are perpendicularly bisect each other. These diagonals bisect each other and are equal. And these diagonals are perpendicular and bisect each other and equal, or however you want to phrase it in there the way it's supposed to be, right? That is a huge chunk of the hierarchy taking care of you with peanut butter every day. Your job, if you choose to, is to come up with something cool to figure out the symmetry lines. You know, I'm not going to give it all to you. You have a brain too. It's like, what's true about the symmetry lines? Then you got a few rando properties that you need to remember. A very tough definition up here in kite that you need to know. You know, that's a hard definition. Tough property right here, you know. Maybe a weird little property right there, you know. But I think it's very, very doable for a class as smart as you guys are. Cool. Let's go do the last questions. Let's draw all the symmetry lines and mark them. I'm going to let you do all 4 of them. Shape recognition, like use the hierarchy, draw all the symmetry lines, work with the neighbor. Make sure you get them marked correctly if things happen. Like if they bisect each other, put the tick marks. If they intersected at 90, put the right angle boxes and all that kind of stuff. So give it a shot. Pause the video, hit that done. Sorry, apparently the worksheet was missing a little arrow right here for this parallel line. That's supposed to be parallel right there. So we got a rhombus on 12, a rectangle on 13, an isosceles trapezoid on 14, and a square on 15. Draw the symmetry lines in. All right. I'm going to go draw them all in and then mark them. I'm going to get my arrowheads going. You should put arrowheads on your lines. So boom, 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 boom. Well, that's way off. Boom, 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 boom. I'm very scared that this is what you're going to put on the test. Close, but no cigar. That is definitely not good enough. We've got to mark them. So let's go back. Here's the rhombus. There are 2 symmetry lines. They are the diagonals. You can't look that up. Shame on you. What's true about them? The diagonals do what? Perpendicularly bisect each other. So boom, 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 boom. Boom, 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 boom. Isn't that also going on being true? Where are the symmetry lines for a rectangle? There's 2 of them, but doesn't it say the perpendicular bisectors of the sides? So you need a right angle box here, 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 here. And to bisect the sides, if this side right here is cut into 2 equal pieces, I should go boom, boom. Got a question on this guy right here. Let me use a different color. Is that red one and the orange one the same length? So since this went single, single, shouldn't this also go single, single? Are you cool with that? Like if that red one is 10, this is 5 and 5. Doesn't this orange one have to be 10? And that's 5 and 5. And then doesn't this have to go double, 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 double? Check your markings on 14 and 15 and see if you want to keep them or change them. On your isosceles trapezoid, it says there's 1 symmetry line, the perpendicular bisector of the bases. So need a 90, need a 90. Question, is Mr. Orange guy the same length as Mr. Blue guy in an isosceles trapezoid? Are they the same length? No. So that's cut into 2 equal pieces. And then what should this one get? Single tick marks or double tick marks? Double A's. And then how about all of this? 90s all over the place. You got perpendicular bisectors of the sides. All of those got to be doubles. Because doesn't a square have 4 equal sides? So if this whole side was 10, then 5 and 5, that's 10, 5 and 5, that's 10, 5 and 5, that's 10, 5 and 5. It's like double tick marks all over the place, man.